Hello and welcome to lecture 25 of Math 2R03. In today's lecture, we're going to be looking at section 8.d, which is kind of the big result of chapter 8 and where we've actually been heading over the last couple of lectures. In some ways, the Jordan form is going to be kind of the most general version that we can get with respect to diagonalization. So remember, not every linear operator has the property that you can find a basis so that the associated matrix is a diagonal matrix. But today what we're going to do is kind of put an end to this story and show that even though you can't get necessarily a diagonal matrix, you can get a matrix that's pretty close to diagonal. And this is what's going to be referred to as the Jordan form. So just to kind of give us a recap of where we are, all right, the story so far, and we've seen this over the last couple lectures, is that if we have a vector space over the complex numbers, and if we take some sort of linear operators, and suppose that we know what the eigenvalues are and the multiplicities of those of this linear operator, then we can find a basis of the vector space so that the associated matrix is a block diagonal matrix where each block is a di by di matrix, where that corresponds to the multiplicity, and then lambda I appears down the diagonal, and we have an upper triangular matrix. So we're getting a matrix over here that has lots of zeros, right? There's a big chunk of zeros over here. There's a big chunk of zeros here. Each of these square matrices have the property that it's lower diagonal, or the lower part is 0, and we have maybe some junk still up here. So we got little upper triangular matrices. Okay. So what we want to do is, can we actually clean this up a bit more so that we can actually reduce the number of non-zero entries in this part? Or another way of saying that is, can we add more zeros? And I just want to make a point here that this matrix here actually has some interpretation. If the matrix here AI has the property that when we take this basis, then the matrix that you get where you just put zeros, replace all the lambda i's with 0, and then you consider the same kind of leftover part in the upper right hand corner, this matrix here comes from the nilpotent operator t minus lambda I times the identity operator restricted to the subspace or the generalized eigenspace of that particular eigenvalue. Okay, so really, in order to improve this result, to kind of clean up all of this extra stuff here, what we need to really do is understand, can we improve nilpotent operators? So this is coming from a result about nilpotent operators. So we really have to focus on this part here, which is going to come from a nilpotent operator. So to improve this result, we want a basis for nilpotent operators so that the associated matrix has as few zeros. Oops, let me fix that. Has as few zeros as possible. Okay, so that's kind of what we're aiming for. So what that means is we have to kind of go back and revisit our result about nilpotent operators and ask, can we find actually a better basis, right? So we need a better basis for nilpotent operators. So that's really what we're doing in today, is just kind of filling in these last couple pieces about figuring out what a proper basis, a proper better basis for nilpotent operators is. So I'm going to state it, and then in the next part of today's lecture, I'll explain why this is in some ways better. But at first glance, it's a pretty complicated statement, right? Because what it says is, take a nilpotent operator, then there exists vectors v1 and vn and v in non-negative integers m1 and mn, such that if you take the nilpotent operator raised to the power of m1 evaluated at v1, that same operator raised to the power of m1 minus 1 evaluated at v1, and so you're decreasing the exponent of the operator for v1. So you're looking, basically what you're doing is taking v1, you apply n to it, you apply n squared to it, and so on, so you get all of these values, and you're doing it m1 times. Then you do the same thing for the vector v2, and finally you're doing this for each of the vectors, and you're also doing it to the vector vn. So you have all of these vectors in numbers m1 to nm, and you have the property that after you form all of these vectors, this is a basis for v. Okay, so that seems complicated. And the other thing is that when you take these vectors v1 to vm, the integers m1 to mn satisfy that if you take n raised to the power of m1 plus 1 evaluated at v1, it's the same thing as n raised to the power of m2 plus 1 v2, and all of these guys are 0. Okay, so one way to think about it is you're finding vectors and some numbers such that you're taking v1, v2 up to vn, that's your first level. Then you're kind of applying n to all of those guys. Then you're applying n to all of those guys, and you keep doing that. But for v1, you stop after you get up to m1. For v2, you stop, you get to n2, and so on. So the claim that this is a better basis, and when we come back from the break, I'll try to explain why this theorem is the better basis, right? And better in the sense that we're going to get a matrix with as few zeros as possible.